Incremental learning is a way of extending the existing knowledge by continuously learning knowledge over time. For example, we can think of incremental learning in classification tasks. Instead of learning all the classes at once, we sequentially learn on new classes. We know we humans can do this easily, however, the modern deep learning failed to do so. After learning on new knowledge, they tend to forget previous knowledge, which we call catastrophic forgetting. And this paper tries to solve this incremental learning problem in semantic segmentation task. So this is an example of pair of image and GT semantic map at its training step, and this is what we want for the final output. As you can see, the model learns on different set of labels with the background at each time step, and it induces new problem. Classes that have seen before or will be seen in future all collapses into the background label, and we call it as background shift problem. So this paper tries to solve those two problems by knowledge distillation with considering background modeling. Before we jump into it, here's a problem definition. Basically, training is done over multiple learning steps, where each learning step introduces novel classes to be learned. Here, we assume that set of labels at different learning steps are all disjoint except the background, which means that once the certain class is learned, then after that training step, the model cannot see that class anymore. And the goal is to train a model f theta that correctly assigns each pixel xi to its semantic labels. To train a model, we can simply try cross-entropy loss as usual, but as mentioned, it suffers from severe catastrophic forgetting since the model will learn on current classes and cannot see previous classes anymore. Common solution is to use knowledge distillation, which forces the model not to forget previous knowledge on old classes. However, we still need to address background shift. So authors modifies those two losses to address background shift as well as introducing proper initialization methods. Standard cross-entropy loss can be written like this, but the background class in current time step might include pixels of previously seen classes. If we don't consider it, predictions on the old classes would collapse into the background as shown on the right figure. So the authors add slight modification. This equation implies that we consider the probability of being either old class or the background instead of considering only that of being background. You would easily understand the rationale if you see the figure with red box. Next, this is a standard knowledge distillation loss. Basically, this loss forces the model to make prediction on old classes with current model to be same as that on old classes with previous models. It forces the model not to forget previous knowledge on old classes. However, since the annotations for background class in current time step might include pixels of future classes, naive knowledge distillation will force the model to predict unseen future class to be background, which is undesirable. So the authors slightly modify this loss to consider the probability of being either new class or the background instead of considering only probability of being background. It's very intuitive and you can easily understand it if you see this example here. So that's all for the training loss, but we also need to consider how to initialize the classifier's parameters for newly introduced classes. We could naively use random initialization, but it will induce misalignment among features since the model at previous time step will likely assign pixels of newly introduced classes to background. This can introduce instability to the training process, so the authors propose to initialize the parameters to make probability of being background at t-1 step to be uniformly spread among the newly introduced classes as shown here. And this can be simply achieved by initializing the weights and biases of fully connected classifiers like this. So this is summary for the overall methods. And let's see the experimental results. For the dataset, these two datasets were used. And for the qualitative result, you can see that the previous approaches tend to predict main classes to be background, where the proposed method accurately predict the labels. And for the quantitative result, they measured mean IOU, which is standard evaluation metric for semantic segmentation. And you can see the proposed method outperforms other baselines with large margins. The experiment on AD20K also shows similar results, and they also performed observation study to see the importance of each components they proposed. And it reveals that all of the components are crucial and contribute to the overall improvement. And this is the conclusion, and this is end of the presentation. Thank you.